Hi, my name is Jim, and the topic for today is nodal analysis. Now, anytime that you see a circuit that has more than one source in it, other than that source being in simple series or parallel, there's a probability you may have to use more advanced circuit analysis techniques, and nodal analysis is one of those techniques. Now, one of the liberties that we can take here, instead of working with the actual numbers themselves in milliamperes, e to the -3, and kiloohms would be e to the +3, is that we can work in MA and K directly, which will get rid of the actual exponent that goes with milliamperes and kiloohms, and all that does is it simplifies our numbers a lot. So depending upon your circuit values, you can do things like this, which will make basically the calculations less subject to error. So we're going to start out and work about 4 examples here, and we're going to be doing Norton conversions in this also, where you can see the power of it and how it can simplify some of the calculations. So to begin with, here we have a 22 volt source in series with a 2K resistor feeding node A, and what we want to do is find the voltage at node A, and once we know that, we can figure out any other parameter in the circuit. That is connected to ground by an 8K resistor, and further we have a 12 volt source, and this is connected to a 3K resistor. So what we have to start with here is to take advantage of Kirchhoff's current laws and assign current flow directions. And I really don't know what directions are valid. I don't know, and we're just going to have to guess at it. And I've assigned current directions of I1 is flowing into node A, I2 is flowing into node A, and I3 is flowing from node A to ground. Now, if I guess incorrectly, what's going to happen is the mathematics is going to come out with a negative, and that means that the physical current is actually in the opposite direction to the current that I guessed. So it'll all work out. Now, looking at this, and with all due respects to KCL, is what we see is we have I3 is going to be equal to the sum of I1 and I2. So I've started by writing that equation at the beginning. Next, what I need to do is find out what I1 is, or I3 is rather, and he's flowing down, so that's simply going to be the voltage of node A divided by 8, and that really would be 8K, but we're working in mils and kiloohms, so it's just going to be 8. And the voltage I1 is going to be 22 minus VA, because of the current direction here, divided by 2K, that's this term, and then I2 is going to be 12 volts minus VA divided by 3K, which is this term here. So I'm going to verbosely work this out and show every single step here so there's no ambiguity. What I'm going to do is break these two down into individual fractions. VA over 8 equals 22 over 2 minus VA over 2 plus 12 over 3 minus VA over 3. And then I'm kind of interested in combining like terms, but first I'll take care of these fractions here. So VA over 8 is going to be equal to 11. That would be this guy, and 4, which would be this guy. And the other terms remain the same. Coming back over here, we have VA over 8 equals negative VA over 2 minus VA over 3 plus 15, where I've combined 11 and 4 to get to 15. Now, what I need to do is combine these two fractions, and to do that I need a common denominator, and looking at this is going to be 6. So VA over 8 would be equal to negative 3 VA over 6. So as what we can see is that if we divide these two out, we end up with the same value here. So that's one of the things we have to be careful of. Taking this term and finding its common denominator, is we have 2 VA over 6, and that's going to be subtracted, or adding a negative, if you will, plus 15, and now we can combine like terms here to give us VA over 8 equals negative 5 VA over 6 plus 15. So, coming back here, we have VA over 8 plus 5VA over 6 equals 15. And oops, where am I at here? Oh, yeah. Or 3VA over 24. And what I'm doing here is combining these two like terms together, and what I need is a common denominator. And the obvious denominator would be 48. However, it's not the lowest. 48 will not produce the wrong answer, but 24 is the lowest. So in converting the denominators to 24, I have 3VA over 24, and what we can kind of see here is if we divide both sides, or the numerator and denominator, by 3, we end up with 1/8, or VA over 8. Likewise with the second term here, we have 20 VA over 24 equals 15, and then adding these like terms together, we have 23 VA over 24 equals 15. So what you can probably see so far is that there's a fair amount of relatively simple mathematics, and you have to be careful about making a mistake in this. So it's good to write down every single step as I have done and not take any shortcuts, because if I get a ridiculous answer here that doesn't check out, I can go back very quickly and see perhaps that I made a mistake in finding a common denominator and things like that. So this is where we are. We'll multiply both sides by 24, giving us 23 VA equals 360, and finally isolating our variable VA would be equal to 15.65 volts. So that would be our voltage here, and now the question is what are the current flow? I have I1, I2, and I3, and I guessed at them. Let's find out if I guessed correctly. So I1 now is going to be 22 minus VA, which is our 15.65 that we just calculated, divided by 2K, and that turns out to be 3.17 milliamperes. Now this is a positive value, which means that my guess on that was correct. Let's look at I2, and that's going to be equal to 12 volts minus VA, which is 15.65 divided by 3K, and that comes out to be negative 1.22 milliamperes. And that means that the physical current is flowing in the other direction. So that negative sign says that my guess on that was incorrect. But the math fixed it right with that negative sign. And then finally, I3, which is really simple, it's just VA divided by 8K, comes out to be 1.97 milliamperes. So my expectation is that all of these currents have to equal I3, and if I add these together here, is what I see is that I end up with 1.97 milliamperes, the same as what I had before. So that's a good safety check. Now it may seem strange that we have a conventional current flowing into the positive terminal of a battery, and all that means really is the battery is being charged. This happens as soon as you start your car, because the battery in a car is called an SLI. That's starting, lighting, and ignition. It's never to be deep discharged. It's not designed to be deep discharged, and you can ruin the battery by deep discharging it. But that would be charging a battery in your car, or better yet, charging a cell phone battery. Now the batteries, or in the case of a single cell, need to be rechargeable, and that's called a secondary cell or battery. If you're recharging primaries, like an alkaline battery, is basically, if it had any charge left, is you destroy it. And the reason is that the chemical energy in it is not reversible with charging, where in a lead acid battery or a lithium ion it is reversible, but not quite 100%, which means you wear out the battery a little bit. So let's take a look at this problem. Some transformations on it here, and these would be from voltage sources into current sources, and if you haven't viewed that video yet, I suggest you do so. And we're going to call this the internal resistance here and substitute in a current source. So taking the internal resistance 2K and placing it across the current source, and then we have to find out the value of this. So what we do is short this out mathematically. Okay to do that in a real circuit, not a good idea perhaps, but that's 22 volts divided by 2K, and that gives 11 mils to our current source, and that's going to flow in the same direction as our current that we specified in the beginning, which would be this direction here. That, okay. Secondly, I have to find out or convert the other source into a Norton equivalent. So my internal resistance goes across that source, and then to find out what the current is, I would simply take 12 volts and divide it by 3K as I did before, and that'll give a value of 4 milliamperes. Finally, combining everything together, this is what it looks like. And I have 3 resistors in parallel, and first order of business is to combine those and end up with 1 resistor. So our total in this case would be 2K in parallel with 8K in parallel with 3K, and that produces a value of 1.043 kiloohms. So VA is simply going to be equal to the sum of these 2 currents, this guy and this guy, times the total resistance, which is 1.043K. So 11 mils plus 4 mils times this value gives us a value for V node A of 15.65 volts, and that is what we obtained before. Now you might notice that this technique has less numbers written on the paper, so it's an easier way of solving the problem, and since there's less mathematics in it, it's probably less likely to make an error. So that's the power of Norton transformations, is to simplify sometimes the solutions that we need to solve a problem. So let's go on and look at another problem here. In this case, what we have is a voltage source and a current source. This guy is 20 volts. I use the same resistor values with a 14 milliampere current source here, and I want to find VA. So I guess the currents again. Assigned I1, I2, and I3. And what I can see here is that I1 is equal to I2 plus I3, because these 2 currents flow out of the node where I1 flows into it. So breaking this down, the value of I1 would be 20 minus VA again, divided by 2K, equals 14. Now I don't have to worry about this resistor. And the reason is this is a 14 milliampere current source, which means 14 milliamperes is going to flow regardless of what the voltage is across the source. It's simply not dependent upon the voltage, nor is it dependent upon any resistor that's sitting in there. If this voltage has to be 100,000 volts to make 14 mils flow, that's what it'll be. And of course, this is a model. So all we have to do in this case is put down the 14. It can't be anything else. Secondly, let's see here, where was I? 14, and then this current here, I3, would be VA divided by 8K again. So breaking this fraction down into 2 independent guys, we have 20 over 2 minus VA over 2 equals 14 divided by VA over our 8K here. And then we'll start to, I simplified this, 10 minus VA over 2 equals 14. Doing everything step by step here. So combining like terms here, again I have an issue with the denominator, and that's going to be relatively easy to do. I have 10 equals 14 plus VA over 4 VA divided by 8. So the only denominator that I have to adjust is the VA divided by 2. Easy to do that. And now we're going to combine like terms. 10 equals 14 plus 5 VA divided by 8. Finally, we'll move the 14 over to the other side, and this gives us a negative 4 equals 5 VA over 8. Finally, multiplying both sides by 8 gives us negative 32 equals 5 VA. And finally, VA equals negative 6.4 volts. So, once we know that, we can go on to find the individual current flows. So, I1 is going to be equal to 20 minus a negative 6.4 divided by 2K, ends up being 13.2 milliamperes. I2, that's easy, 14 mils. I3 is going to be negative 6.4 divided by 8K, which turns out to be negative 800 microamperes, and I've written that as negative 0.8 milliamperes. Now, the sanity in this is if you add these two together, you see you end up with our negative 0.8 milliamperes. So that kind of looks good. I'm happy with that. Now, let's do the same thing, except we'll convert this voltage source into a current source. And to do that, I'll take the 2K and put it in parallel with the source here again, and the value of the current source will be 20 volts divided by 2K, which gives 10 milliamperes. And this is the circuit that I end up with. I'm interested in RT, and RT is only going to be comprised of these two resistors right here. So that's 2K in parallel with 8K, which gives us 1.6K. So the voltage across DA is going to be I total times 1.6K, and I total will be 10 minus 14 milliamperes. So this is going to be the 10, and we're subtracting from that 14 milliamperes times the resistance of the circuit, and that gives us negative 4 milliamperes. So the current is physically flowing up. So my guess on this guy was incorrect. So if we add this current to this current, is what we get is 14 milliamperes. So again, the sign saved the day by showing it was negative, meaning that my guess was incorrect. And multiplying that out, is what we see is that VA equals a negative 6.4 volts as it did before. So I'm happy with that conclusion. So when you work these problems, take your time, write things down, go slow, double check your answers, so on and so forth. Just be careful not to slip anything, and go back and look over to see if you made a mistake. So that'll conclude, and thank you for watching.